Okay, so solve for x. Like so many others, it's an equation, so I could graph the left and the right, see where they intersect. But let's see what we can do by hand. Okay, this is in exponential form. There are just three players: the base of the exponent itself, and the other side of the equation. Nothing else. So I can convert that to log base 4 of 8 equals x minus 3. And then I can add 3 to both sides. Now, notice, you might interpret this as, well, is all of this being plugged into the log function? No, it's not. So I'm going to go like that just to make it clear what's going on. Okay. And let's see. Now, I can't go any further without a calculator if I do it this way. Okay. And everything I've done is legit. But here is an alternative way. This is the way Alex really wants you to do it. They've set it up for you so that you can do the whole thing by hand without even going to a calculator. They set it up so that you can rewrite both of these numbers as some number, and the same one for both, some number to a power. Well, I can write 8 as 2 to the third and 4 as 2 to the second. So I have that. I could do that. Now they both have a base of the exponent of 2. And so power to a power, I multiply them together. And then I can say, like we saw in the last video, hey, since these bases are the same, the exponents must be the same. So I get that. Add 6 to both sides. Divide by 2. And I get 9/2 or 4.5. And that's how you do it. Okay, that's how you do it by hand completely. But you can always double check it on your calculator. All right, so here's a different one. Now this time, looks like we got 4 players. We got 1, 2, 3, 4. Now there's different ways this can be handled. I've got my favorite way. But no matter what you do, you're still going to have to go to the calculator for it. So here's the way I like to do it. I like to say, you know what? Ever since the beginning of time, you and I have known that whatever you do to one side of the equation, you do to the other. So you can do whatever you want, as long as you do it to both sides. Well, I'm going to do that. I'm going to take the log of both sides. Now, why in the world would I do that? Well, because of rule number 3 of logarithms. Exponents can come out front. So I can pull the exponent out of each of these. Why is that important? Well, because now the x, which was originally in the exponent, how do I handle that? It is now outside of the exponent, outside of the log, where I can work with it more easily. Now, it doesn't mean that the problem is easy, but it's certainly more accessible. Okay. So next step, let's get rid of these parentheses because that's just really bugging me. Okay, so 8x log 13 is negative x log 5 plus 7 log 5. Okay. Now, we're not going to be able to solve for x as long as there's more than one x in the problem. So I'm going to send that to the left side. I'm going to add that to both sides so that we get 8x log 13 plus x log 5 equals 7 log 5. Okay. Well, I think intuitively it makes sense to get them on the same side if we want to only end up with one x, but now what? Well, I'm glad you asked. Here's what. Think of the f word. We're going to factor an x out of both of these terms so that we get factor out an x, and we're left with 8 times log 13 plus log 5 equals 7 log 5. And now only one step left. We will divide both sides by whatever's being multiplied by x. Because remember, you can plug all of that into the calculator and just get a single number. So it's really just a number times x. So we'll divide by 8 log 13 plus log 5 on both sides. 13 plus log 5. Okay, so that cancels, and you just get x on the left, and you get this big boy on the right. So on this one, it says go to the nearest thousandth, which means plug this into the calculator, like we said before, and then round it off to 3 decimal places, nearest thousandth. Okay, and since the author has already got that done, I'm just going to look at their answer. How about that? Oh, here we go. 0.509. Okay, so 0.509 when you plug it all in. That's how it's done. Now, if this were a different topic, which I think is the next one, let me just kind of double check. Well, that's hard to read. You know what? Let me do some erasing. That is really hard for me. Okay, so the next topic, oh, no, it doesn't ask you to do that. Okay, well, anyway, sometimes they'll throw a topic at you that says, do the same thing as this, but give the exact answer. You'll see the words exact answer. And if that's the case, then you stop at this point. You don't plug it in the calculator. Okay. You just stop right there and say, that's my exact answer. That's as far as I can take it. But this one, they want us to go to the calculator. So you would do that. All right, so let's do some compound interest. Now, this time, the compound interest isn't being compounded annually, as in one time a year. It's being compounded something else, okay? In this case, quarterly. Well, how many quarters are there in anything? Well, there's 4 quarters, 4 times a year. Okay, so we're going to want to just use our compound interest formula, which is this. Okay, where P is the principal, the beginning amount, so that's $3,000. A is the accrued or accumulated or final amount, so that's $6,450. 1 is 1. The interest rate is 10%, so pretty big interest rate, so 0.10. Quarterly, okay, N, that tells you how often it's being compounded in 1 year, so 4 times in 1 year. And the question is, how long is this going to take? I don't know. Well, let's see what we can do. I've got a variable in an exponent, so I'd like to convert to log form from exponential form, but we're not in exponential form yet. There's the base of the exponent, there's the exponent, and there's the other side of the equation. But what about this guy? There's a 4th player, so we're going to divide both sides. Oh, dang it, did it again. Divide both sides by 3,000. On the right, they cancel. And on the left, let's see, 6,450. On the left, we get 2.15. Let's see, what's 0.1 divided by 4? Okay, and then inside the parentheses, that tidies up to 1.025. Okay, now it's an exponential form, and I can convert to log form. So log base 1.025 of 2.15 equals 4t. Divide both sides by 4. And let's see, nearest hundredths. So why don't we do this one on the old calculator? Okay, so I'm going to make a big old fancy fraction. And the numerator is going to be alpha window 5 base 1.025 of 2.15, all of that over 4. And it says about 7 and 3/4 years, 7 years, 9 months. Okay, and this said nearest hundredths. Yeah, so 7.75 years. Does that answer seem reasonable? Yeah, I mean, it's not like, hey, in 2 months, your money's going to more than double, or it's going to take 200 years or a negative amount. So yeah, this definitely seems reasonable. And that's how you do it. But for these, like I said, you want to be using that compound interest formula. Now, if it said interest is compounded daily, well, then n would be 365 instead of 4. If interest is compounded monthly, n would be 12. And that's how you do it. All right. Finding the rate or time in a word problem on continuous exponential growth or decay. Key word there, continuous. All right. So usually when you're dealing with just sort of a general exponential growth or decay problem, you're going to be doing y equals ab to the x or to the t, or whatever. But when you see continuous, you are going to be using a different one. Y equals cert. Okay. This E, that's the same one that is approximately 2.7, and it's part of the ln and all that. So that's not a variable. It doesn't vary in value. It's fixed. C, that's the same. Oh, oops, let me give it a circle. C is the same thing as the A. It's the y-intercept. It's the beginning amount of whatever you're talking about. T is still time. Okay. And R, well, that's the growth or decay rate. Okay. So for this one, we know that we want cert because it says continuous. All right, so that's one. That's a nice thing to just kind of narrow it down fast. Okay, so the number of bacteria in a certain population increases, so it's getting bigger. So that tells us that our R value is positive, not negative. According to a continuous exponential growth model with a growth rate parameter of 1% per hour. So how many hours, so we're solving for t, does it take for the size of the sample to double? All right, so using our cert equation, let's see. It doesn't say what we start with. So I'll just start with C, I guess. You could pick a number if you want. It really won't matter. I'll just pick C because they don't tell me how much it starts with. And it says growth rate parameter of 1%, so 0.01 times t. And it says, how long is it going to take for it to double? Well, if we're going to start off with C bacteria, then we're going to end up with double that. Okay. Or maybe you said, I want to start with 100. Okay, then this is 200. It won't make a difference because the next step is divide by whatever that is. And when you divide by C, those cancel, and all you're going to be left with either way is a 2 on the right side. Now that this C is not there, we can convert to log form, get log base E of 2 is 0.01 t, divide both sides by 0.01, and it says go to the nearest hundredth. All right, so I'm going to do ln of 2. Actually, I'm going to turn on my calculator first because that'll work really good. ln of 2, and then divided by 0.01, and that gives us 69 and nearest hundredth, 0.31. 69.31 what? Let's see, exponential growth. What's the growth? Oh, we're measuring in hours. So 69.31 hours. That's going to take almost 3 days, just about 3 days for the population to double. Wow. Bacteria definitely reproduce faster than humans or even rabbits. Okay. But that's how it's done.